So when you are trying to work with collision elasticity, you are dealing with the energy involved in the collisions. So for this first question, how do you know that the collision is elastic if it goes back to the same height? You need a response that ultimately talks about kinetic energy, right? So we need to link this to energy conservation. So if they go back to the same height, here's the progression that we need. The same height means that they must have the same gravitational energy between the first bounce to the second bounce, right? So the gravitational energies must be the same. If the gravitational energies were the same, that means that the kinetic energy before and after the collision must also be the same. If the kinetic energies were the same, then you know you have an elastic collision, right? But your elastic collision ultimately needs to work itself through an explanation that deals with conservation of kinetic energy, right? So you need something that deals with conservation of kinetic energy. For the second question, if it's only going 75% of the way up, now we do not have the same gravitational energy, all right? We lost some energy, and that energy loss, so we generated some sort of thermal energy in the bounce, and if we generated thermal energy, that means that the kinetic energy is not conserved. All right. So if you're generating thermal energy in the bounce, then that means that your kinetic energy was not the same before and after. Any questions on this concept right here? Yes?
Good answer, right?
Fantastic. Just stunning. Any other questions? All right, we got one, just a couple slides of notes to look at, and then we ready to wrap this up. So we'll give you a minute to write this down, and then we'll talk about a couple of the items on here. So when you are working with collision elasticity, we are dealing with the kinetic energy conservation in a collision. Momentum is always conserved in a collision as long as you set up your system correctly. However, kinetic energy is not necessarily conserved. The elastic collisions will frequently have objects that bounce, that move in opposite directions. This is a general trend, not precise. You can get elastic collisions that don't do this, but this is something that you'll see more often than not. And there's no magical way to figure out if a collision is elastic or inelastic. What you have to do is simply calculate the amount of kinetic energy before and after the collision and look at the system totals before and after. If it is equal, then your collision is elastic. If they are not equal, then your collision is inelastic. For the purposes of this class, we're going to look at this as sort of an either or. If you want to do a little bit more in depth with this, elasticity is really on a spectrum that ranges from 100% conserved is considered totally elastic, and 100%, if you lose all of it, if your objects come to a stop, then that is considered totally inelastic, where you lose all of your energy. But there's a lot of range in between this, and this formula, this is beyond the scope. We're not going to actually calculate elasticity percentage, but if you take the amount of energy lost, that's this top part, like your final minus your initial, and divide it by your initial total, you multiply by 100 to get a percentage, but this will tell you the percent elasticity of a collision. So something that retains most of its energy could be 90% elastic, 95% elastic. Objects that bounce very well, you can measure how well they bounce by looking at the kinetic energy conservation in these bounces. So things like golf balls, lacrosse balls, depending on how you inflate like a basketball, volleyball, you can actually measure elasticity as a function of how much kinetic energy does it maintain in a collision. And you know, any of you that play inflated ball sports, if you start having a deflated, volleyball, soccer ball, football, whatever, you're Tom Brady, you like things on a little deflated side, then it just doesn't feel quite right. Okay, you start losing elasticity and it doesn't bounce as well. So what we're going to do now is we're going to look at a sample collision here. We're going to evaluate, is this elastic or is this not elastic? So this is going to be a two-part thing. First thing we need to do is look at the collision itself. So we're going to use conservation of momentum first, and then we're going to look at conservation of energy second. All right, so this first part right here, we've got our red car is moving, listed 5 meters per second, hits our blue car that is not moving. We have masses for each of them. What we're going to do is, based on this, we need to find the velocity of the red car after the collision. All right, so it says the blue car moves forward at 2.5 meters per second after the collision. Can we find the velocity of the red car after the collision? All right, so this first part is going to be a conservation of momentum. After we do this, then we can look at the kinetic energy of each car before and after, look at the system total. If they are the same, then we'll say yes, this is elastic. If they are not the same, then we'll say no, this is somewhat inelastic. I'll get you started and we can finish this. So basically we're doing red is moving. So this will get you started. You got your red and blue car as your system before and after the collision. We know the red car is initially moving, blue car is not. After the collision, we know blue car rolls forward, red car, we're not really sure where it's rolling. That's what we're finding out, so this is our unknown. We know that the total system momentum before is equal to the total system momentum after. So let's see what we can do from here and find our unknown velocity of our red car post-collision. Once we do that, we can look at our energy conservation. In case you forgot, kinetic energy is 1/2 mv squared. Let's do this. So this is here's a good solution here. We've got the momentum. So here's momentum of red car plus blue car equals red car plus blue car. We have unknown final velocity of blue car after the collision. And then this works itself out to minus 2.5 meters per second. All right, so this is good. So which direction is this car going? Right, it ends up going backwards, right? That's interesting. So this is going to end up going backwards after the collision at 2.5 meters per second. So the second part of this, is this collision elastic? How are we going to figure this out? Right, so in order to do this, we basically are just going to do 1/2 mv squared plus 1/2 mv squared, and then we're not sure if it's equal or not, but that's what we're going to figure out. 1/2 mv squared plus 1/2 mv squared. So again, we have blue plus red is or is not equal to blue plus red. Let's finish this up. This will be our last thing for the day.
Why are we doing this?
So your kinetic energy in this scenario, before the collision, you end up with 12.5 joules of kinetic energy. It's all in the red car. And afterwards, I believe this is this 3.7,
3.125.
3.125 plus 6.7,
9.375.
9.375. 9.375. And so that is also 12.5. So these are equal to each other. So this is elastic. The thing you have to be careful of when you are doing kinetic energies, energy is a scalar, right? Unlike momentum, the negative signs that you get in your velocities do not make kinetic energy negative. There is no negative kinetic energy. So even an object that is moving backwards, that is positive kinetic energy. If you are careless on your calculators and you type in negative 2.5 squared, sometimes your calculator will put the negative sign after it does the squared, and it will tell you that this is negative. So you need to make sure that you are the master of your device is not the master of you. Because if you are not careful, you can get a negative answer here from your calculator, and then you will say, well, it's not conserved because it's only like 6, all right? And then you would be wrong, all right? So watch that, and you're in good shape. Have a good one.